Policymakers and researchers analyzing randomized controlled trials (RCTs) increasingly harness satellite imagery to capture the geographical, socioeconomic, or environmental covariates believed to moderate an intervention's impact. Some of those moderating factors might be locally confined, such as how building density around a household corresponds to labor market opportunities. Others might be more zoomed out, capture broader roads, farmland, or neighborhood features. But an immediate question arises: what scale of satellite imagery is best for capturing these patterns? If you only look at a high-level big map for each participant, you might miss the distinct micro-characteristics that matter for an individual's response to treatment. Conversely, if you focus too narrowly, say, only the 50 minutes radius around a household, you risk ignoring a bigger neighborhood context. And yet, it is not always the largest possible image that yields the best results. This tension, sometimes called the multi-scale problem, motivates the approach here to concatenate or append data from multiple scales, systematically investigating how many and which scales help detect effect heterogeneity in an RCT. In what follows, I describe how we tested these ideas in 2 large anti-poverty RCTs, and then summarize how the results, repeated across different scales or different zoom levels, show that multi-scale analyses consistently outperform single-scale analyses, yet only up to a point. We observe that the returns to concatenating more scales eventually hit diminishing returns around 5 or 6 scales. Below, I also excerpt exact figures from our paper that illustrate these patterns numerically. Background and motivation. The impetus: in satellite-based heterogeneity analyses, we typically feed a single-scale imagery, say, a 128 pixel patch, into a machine learning model that tries to predict who benefits most from treatment. The outcome might be, for instance, post-treatment consumption, health status, or savings. By multi-scale, we mean that we fetch additional images of different sizes. For example, 32 × 32 for a tight focus, 128 × 128 for an intermediate focus, and 256 × 256 for a more global vantage. The representations from these images, extracted by a neural net or other encoder, can be concatenated into one big vector. Intuitively, that single vector might better reflect the interplay of the small-scale immediate environment and large-scale contextual environment drivers of heterogeneity. A single small-scale patch might omit important signals from the broader neighborhood. A single large-scale patch also often blurs out or dilutes relevant local detail, ironically reducing the sharpness of the household-level signal. Concatenating multiple scales, each capturing distinct vantage points, can mitigate these weaknesses, until, ironically, too many scales produce overhead and noise. Scaling laws for multiscale dynamics? If multiscale dynamics are operational, how do they scale? In other words, how does concatenating representations from more and more scales affect performance? We look into this below. We examine how the rate ratio, one measure of how strongly an RCT analysis detects and ranks effect heterogeneity, changes with the number of concatenated scales. We see a distinct upward slope until about 5 scales, at which point it plateaus. From the figure blue line for Uganda, light blue for Peru, black for overall average, it is evident that going from 1 scale to 2 scales shows a marked improvement for both Peru and Uganda as well as the overall mean. By the time you reach 5 or 6 scales, the line more or less levels off, especially in Peru's curve, with only mild improvements from scale 4 onward. In effect, the law of diminishing returns sets in after about 4 or 5 scales. Multi-scale representation concatenation helps, but it saturates once most vantage points are included. Interpretation? There seems to be a scaling law for how multi-scale imagery helps affect heterogeneity detection. It rises rapidly, but saturates once the model has had enough vantage points to ensure that it likely covers the optimal zoom, or includes synergy across different local neighborhoods. In short, bigger images alone are not always better, but multiple vantage points from small to moderately large scales often pay off. 2 interpretations of the multi-scale benefit. Why do we see improvement with multi-scale approaches? One possibility is that one scale is best for the data, but we do not necessarily know which. By stacking many scales, we are more likely to stumble onto that optimal zoom factor. But if that were the sole explanation, then we might expect the performance to level off more quickly once that single best scale is included. Instead, we find further incremental gains with each extra scale, through scale 3, 4, or 5. Thus, a second explanation, Truly different vantage points supply complementary information about effect heterogeneity. A multi-scale approach can exploit synergy among the local household-level imagery, the immediate neighborhood imagery, and a more global context. Indeed, in the Uganda dataset, local household scale 16 times 16 patches alone are rarely enough to detect, say, presence of farmland or roads just beyond the immediate boundary. Meanwhile, extremely large patches, say 349 times 349, might capture roads but wash out the subtle differences in roofing materials, a proxy for household wealth. By concatenating them, the multi-scale method balances fine-grained signals and broader contextual signals at once. Implications. In practical policy terms, these results suggest that if the computational or data cost of obtaining multiple imagery patches for each observation is modest, you should strongly consider it. Gains can be significant if the researcher's existing single-scale pipeline is missing relevant detail. Note, however, that after about 4 or 5 scales, the improvements do taper off, so it's not a simple throw bigger images at it approach. Methodologically, we see that the presence of multi-scale signal in satellite data is pervasive, but not infinite. Large images alone can underperform smaller ones, highlighting that bigger is not automatically better. Combining multiple vantage points is helpful at first, but eventually saturates. In sum, these multi-scale findings enrich our understanding of how best to glean treatment effect heterogeneity from Earth observation data. Our analysis in the Peru and Uganda RCTs underscores that there is not a single optimal scale for capturing effect moderating features. Rather, synergy across a handful of vantage points is both feasible and beneficial. We might consider it a modest but robust demonstration of scaling laws in effect heterogeneity detection, with important ramifications for anti-poverty policy targeting, environmental analyses, and future high-resolution observational datasets. Future research might refine the method by adaptively choosing the right scales for each participant. For example, if a local household is near a city boundary, you might want a bigger vantage than if they are in an isolated rural region. Precisely how to do this is not yet obvious, but the consistent improvement from multi-scale approaches points to a promising frontier.